we just complete a famous algorithm. Its name is sieve of array things. Yeah. An ancient Greek algorithm. Yeah. Very simple, yeah, but effective. Yeah. All right, we complete the details of the sieve algorithm. Now we need to write the code. Yeah. Yeah, here we just do the pseudocode. Yeah. All right, 8.4. This algorithm, we call it trial division. Yeah. Because we need to do a lot of division trials. All right. Yeah, so let's look at the, we modify, yeah, because last time, near the end of the class, basically we did analysis part. Yeah. So the main ideas, main, algorithm part, but that's the analysis part. In our coding, yeah, so we need to modify a little bit. Yeah. So here, yeah, one modification is we change from multiplication to division. Yeah. In our analysis, we use multiplication, right? Yeah. Yeah. When we check the composite numbers, yeah, here. Yeah. So remember, so the main formula we use to check the composite number, n equals a times b, the product form. Yeah. But in our implementation coding, yeah, so we will use its equivalent formula, b equals n over a, division. Yeah. So we just do division trials. Division trials. Yeah. Why? So what's the difference? Why we do this modification? Yeah. The reason is very simple. If we use the original multiplication formula, you need to have both a and b, right? You need to have the values of these two parameters, a and b. Then you can apply a multiplication, then compare it with n. Yeah. But when you choose two variables, technically, you need to consider two things, right? Two objects. Two objects. The two objects here are the two operands, right? Yeah, multiplication. One multiplication, you need to use two operands. All right? Then, now, we convert it to equivalent division formula. Now, this time you can see you only need one parameter, a, because n given. N given, yeah, so it's known. We use it directly, yeah. So we do not need to do anything when we use n. So we only need to determine the value of a, then we can apply division operation to do the checking. Yeah. So when we do the division operation, at the same time, we also do the checking. Okay, all right. So then here, another round modification. Yeah, modification. So here, you can see, when we do the division here, the quotient is not important. Nobody care about the quotients. Yeah. So people only need to know if the division here is an integer or not. Okay? Yeah. So what people want to know is the a over n over n is an integer or not. Okay? Yeah. As for the value of the integer, it's not important. Yeah. Yeah. Not important. Yeah. All right. Based on this observation, then we modify another round. So we only want to look at we skip the quotient part. Yeah. We don't need the quotient part. All right. So we just do the modular m mod a. Yeah, so this percent sign, we know it's a modular operator. M mod a, and this, yeah, too sensitive, yeah, messy. Yeah. So this expression gives us the remainder. Remainder expression. Okay? Yeah. So we only need to look at the remainder. And we skip the quotient. Not important, quotient. Yeah. But when you look at the remainder, if the remainder equals 0, it tells us n is a multiple of a. And also, n over a is an integer. That integer corresponds to b operand. Yeah. But if the remainder is non-zero, then we know n is not a multiple of a, right? Yeah. So if the remainder non-zero remainder, right? Yeah. So the conclusion, n is not a multiple of a. Yeah? All right? So that's our interpretation. So we switch to trial division and we do this interpretation. Okay? Equivalent. But you can see this division way is much better than the original multiplication way. Yeah. So in your coding, you need to do a lot of improvements. Yeah. All right. So after this step, now we are ready to look at the pseudocode. Yeah. All right. So here, yeah. So we already this time we need to consider a. Okay. Yeah. So when we select smallest prime factor in the range, that's our a. After we get this a, then we do the modular operation, remainder, and check if it is 0 or not. Yeah. So this is the range. Yeah. Last time we discovered the range for a. Yeah. So this is the range for a. Okay. Yeah. Yeah. Actually, based on our analysis, a should be the primes in this range. Primes in this range. Yeah. Because we skip all the composite numbers in the range. This range contains many composite numbers. Yeah. So when we do the testing, yeah, we want to skip all those composite numbers for a. Yeah. All right. So now, implement the following steps. Yeah. Trial division. Select the smallest number p in the list. Yeah. So this is the list, right? Yeah. In the list. Yeah. That has not been tested. Yeah. Because when we do the testing, we follow the natural order from the smallest prime number in the list, then increase the number gradually, one by one. Yeah, you know, yeah. All right. Then we apply the modular operation, M mod P, and check if it equals 0 or not. If it equals 0, it tells us P is a fact. Yeah, add P to the factor list. Yeah, yeah, right. Yeah, so add P. Yeah, so here, add P to the factor list. That means this P is a factor of N. So this is a factor of N. Okay? Yeah. Oh, so here, yeah, so let me explain a little more. Look, currently what we are doing, we do prime factorization, right? Yeah. So what we are doing is prime factorization. So the output, what is output? A list of prime factors of n, Yeah. So add to the factor list. Yeah. So that's the, you know, output. Yeah. So we add it to our output list. Yeah. All right. Yeah. And set n equals n over p, the quotient. Yeah. Because we find a factor, so we take it out. After we take it out, the remaining part, the quotient, n over p, that's the quotient. The quotient is the remaining part after we take out the current prime factor p. So, yeah. So next round, we keep taking out more factors from the current variable n. Yeah. Here, we use this n variable. All right. Yeah. Yeah. Repeat the process. Yeah. So then we do the modular operation. You know, if if the remainder is not 0, then that means this current p is not a prime factor, right? It's not a prime factor. We bypass it. We go to the next p in the list, in the range. So here I want to separate. So this is the range. The output is the list. Okay. Yeah. So we don't want to confuse them. Yeah. So we go to the range to pick the next p value. Then keep doing this same process. Yeah. All right. Then at the end, so after we finish processing the whole range, the numbers in the whole range, so we need to generate the final result. Because at the end, we have this whole output list, but we need to give the prime factorization of the given number n. Yeah. After we finish the testing list, I'll put the factor list in certain format. Yeah. In a certain, why certain format? Yeah, because if different people use different format, it's hard to do comparisons, right? Yeah. Because sometimes people need to compare two prime factorizations. Yeah. So people want to use some standard format. If everyone uses standard format, then you can compare. Now, using the standard format, then you can, compare factor by factor. Yeah. And you can do operations based on the standard form. Yeah. All right. All right. Yeah. So before I go to the next slide, let me give you an example. Yeah. Example. Greatest common divisor. When people find the greatest common divisor of two numbers of m, and n, we know we can do prime factorization of m and n, right? So when you do factorization, you want to use the standard form. Then you process standard form of these two factorizations, then you can find out the greatest common divisor, right? Yeah. Otherwise, if you do not use the standard format, when you want to compare the two factorization forms, you can get very messy. Okay, so that's the reason the standard form is important. Yeah. This greatest common divisor topic, we will talk about it in module 3. Okay, yeah. So here I just use it as an example. Yeah. In module 3, we will talk about the algorithm calculating the greatest common divisor. Yeah. All right. Now look at the standard. What's the standard form? Yeah. So there is a famous theorem in number theory. It's called the unique factorization theorem. Yeah. So that tells us if we use the standard forms, if we need to define that standard form. If everyone uses that standard form, then the factorization is unique. Okay? Now, then you can do comparisons. Yeah. All right. Any positive integer can be written as a product of primes in one and only one way. So that's important. Yeah. Standard way. Yeah. Under the standard format, then it is unique. Yeah. It is fixed. One and only one way. Yeah. So what's that standard form? We call it prime power decomposition. Yeah. Each positive integer can be written in exact one way in this form. This is the specific form. P1 to the E1 times P2 to the E2, and so on. Yeah. And the base numbers, P1, P2, they are prime numbers. Yeah. So they are prime numbers, and we know we arrange the prime factors in ascending order. Yeah. So then, E numbers greater or equal to 1. Now, cannot be 0. Yeah. 0, yeah. So we remove it. Yeah. So this is the standard form. And we call it prime power decomposition. Yeah. And you can always do for any integer, positive integer, you can do this way. So that is the unique factorization theorem. Yeah. All right. Yeah. Yeah. All right. Now, let's write the pseudocode. So this is pseudocode. Okay, all right. For the pseudocode, yeah, algorithm, input, only one integer. Yeah. So you only need one integer as the input. Output, list f of prime factors of n. Yeah. Okay, all right. Yeah. So you do initialization. Yeah. All right. Yeah. You need to, determine the range for the primes. Yeah. Then you run for loop. Yeah. For each prime in P range, yeah, that P set. P is a set. Okay. Yeah. Do trial division. Yeah. So inside the for loop, you do trial division, while n mod P equal to 0, you add factor P to the list F, then you update that n variable by the quotient number. Okay, all right, yeah. So here you can see the same prime P could be repeated multiple times in the list. Yeah. Yeah. So don't worry, even multiple times. So you collect, yeah, all the multiplicity of that P in the list. Yeah. All right. So at the end, you need to do conclusion. Yeah. If F is empty, yeah, because when you do the trial division, you couldn't find any prime factor, yeah, until you reach the end. Then what's your conclusion? Yeah. Because in that way, that means n itself is a prime. Yeah. N itself is a prime. So you need to add it to the list F. Yeah. And your conclusion is the current n is a prime number. Yeah. So that's all you need. Okay? Yeah. Otherwise, if list F is not empty, that's your factorization. That's your prime power decomposition form. You can use it to do other operations, like a GCD, greatest common divisor, GCD. You need to use it. Sometimes, not always, yeah, GCD. Yeah, later we will, look at different ideas for GCD. Yeah. All right. Yeah. Then the last thing. So before we finish this part A, I want to make comments. The last thing here. All right. Determining the prime less than or equal to root of n is not a trivial task as n gets larger. Yeah. So what's the meaning of that? Because, yeah, think about, look at this line. When we select a little p, yeah, this little p is supposed to be a prime, right? Supposed to be a prime. That means we should skip any composite number. We only take prime. Yeah. But when you do that, it is not easy, not a trivial task. You need to do a lot of work. So this not a trivial task means need to do a lot of work. Okay? Yeah. People need to do a lot of work. Yeah. So when you do a lot of work, there is a cost associated with it. Yeah. The cost here, computing time. We need to spend time, CPU time. It takes time to do that work. All right? Yeah. Then, so there is a question. Is it worth the extra work? Yeah. Because when you do it, you need to use your computing resource. And you need to slow down your algorithm. Yeah. For that part. Yeah. It may not be worth it. When you do that, it may not be worth it. Okay? Yeah. 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 Sometimes, yeah, we need to make the decision here. Do we want to do this special task? Yeah. All right. So then, so people feel there is a simpler way. Yeah. Actually, it can save us some computing resource here. So what's that? Yeah. So, yeah. Simple computer program to factor number, just try successive integers, right? That means you just go through the list, 2, 3, 4, including composite number. You still do the trial division. Even if you get a composite number, you still do trial division. It doesn't hurt. Okay? It doesn't hurt. Although it's redundant. Yeah. We know when you do the trial division on composite numbers, it's redundant. Yeah. But it doesn't hurt. 5, 6, also composite number. Okay? All right. Then the last one, root of n. You just work on the whole list of numbers in the range following its natural order without doing any work to remove these composite numbers. Don't do it. Because when you do it, you need to spend more time. Not worth it. The extra time you use to remove all the composite numbers, not worth it. Okay? Yeah. So then, in this way, you can simplify your algorithm. Now, actually, you can make your algorithm a little faster. Little faster. Yeah. So that's the comment. Yeah. Yeah. So with this understanding, yeah, so we can get a, pretty good understanding on that sieve algorithm. Yeah. So this is this. Yeah. So this is related to sieve. Okay. Yeah. So they're related to sieve, but it is not a sieve. So we call child division. Yeah. Related to sieve. Yeah. Yeah. All right. So that's the part A. So now I want to jump to part B. Yeah. Oh, yeah. Another thing, before I jump to part B, one more thing I want to say. Yeah. So why I talk about, although for this part A, so I want to give you some initial impression on problem solving for computing problems. Yeah. But this one, this prime factorization, this one, yeah. Remember, in the previous slide, I mentioned in Module 3, when we learn the topic of greatest common divisor, we will apply prime factorization again. So at that time, yeah, I will give you an optional project. Yeah. Optional project. Yeah. The optional project, you compare two algorithms. The first algorithm, you do GCD based on prime factorization. That's the first one. Okay? Yeah. GCD. The second algorithm, so that's the one we will learn in module 3 based on recursion. Yeah. Recursion. Yeah. So then we compare these two algorithms. Which one is faster? Which one is slower? Okay? So since it's optional, not required, so I give you extra credit. So if you want to spend your precious time on it, so the extra credit, you will get a 2%. This 2% is the overall 2%. Yeah. Yeah. So here, just to let you know, yeah. Because at this point, yeah, we're not ready for this optional project. We need to wait until we complete module 3. Yeah, module 3. Yeah, so yeah, not necessarily complete module 3. Halfway of module 3. Yeah, first half. After we complete first half of module 3, then we can work on this optional project. Yeah. All right. Yeah. Next, let me get out. Part B. I need to change my pen color again. All right. The title, Efficient Polynomial Evaluation. Yeah. So this topic, yeah, just let you know, that's the topic for our first programming project. So after this lecture, so then we are ready to do our first programming project. All right, so let's look at this topic. B.1, evaluate the polynomials. Yeah. So it's a simple question, but there are many different ways to evaluate the polynomials. All right. Question first. Data. The given data is one polynomial. All right. So the standard form of polynomial is like this. Yeah. A0, A1, an array of coefficients given. Okay? All right. Given as an array. All right. And x is a variable. Yeah. So you can choose different values for x variable. Then you evaluate this given polynomial. Yeah. Question. How to evaluate the polynomial efficiently? All right. That's our computing problem number 3. Yeah. All right. Yeah. So here I give you the reference in chapter 6, section 5. Yeah. It's in a later chapter. Yeah. The reason I choose this topic, first, it's not hard to understand. Yeah. Evaluate polynomials. Everybody knows how to do it. Yeah. And the technique we will use, yeah, we can understand easily. Yeah. Second, because it's a good topic for programming project. Yeah. So that's the reason. Yeah, because we want to do our program project as early as possible, especially for this short semester, 8 week short semester. So we want to start as early as possible. Yeah. All right. First try. Yeah. So let's, try to find a solution. Yeah. If the solution is good or not, we don't worry about it at this point. Yeah. We just want to find one solution at the beginning. Yeah. All right. Here we want to use the straightforward algorithm. Right. Because here you can see basically what we need to do, just the multiplications and additions. Right? Yeah. And we all know how to do multiplications and additions. Yeah. So let's just do it. Yeah. So, all right. To get the sum of all the terms, yeah, first let's calculate individual terms. Yeah. Yeah. So each term, here we pick a representative. This is the representative term, a general term. Yeah. Okay? Yeah. A sub k times x to the kth power. Yeah. Question: how many multiplications do we need? Yeah. It's a simple question. Okay? Yeah. Can you see? Yeah. So for this small problem, sub-problem, can you see? If k is given, so k could be 3, could be 5. If k is given, can you find the answer in terms of k? How many multiplications to calculate this one? Yeah. All right. So you can guess, based on your intuition. Yeah. So based on your intuition, because it's a simple question. Yeah. Can anyone type your answer in the chat area? Just guess one. Because in our problem solving, many times we need to do a lot of guesses. A good guess is important. When we do a guess, we do not require our guess always correct. Sometimes it may not be correct. But we want to make our guess as close to the answer as possible. Now, can anyone make a guess? Just make a guess. Yeah. It's an important step in problem solving. Okay? Guess step is important. Later we will do a lot of guesses in our problem solving. Okay? Yeah. So nobody types a guess. All right? Yeah. All right. Yeah. So here, let me introduce some counting method here. All right. If you have no idea, so there is one strategy we can use in this situation. So why you are hesitate to give a guess number? Yeah. The main reason is because you do not know the k number, then you do not have the confidence to make the guess, because k can change. When k changes, so you may feel the answer could be very complicated. Yeah, so that probably the reason you don't want to make a guess, because you do not have the confidence. Okay? All right. So then, let us do some work to improve our confidence. Yeah. So the psychology in problem solving, the psychology is important. So we need to work on our psychology in problem solving. Okay, all right. So we need to collect some more useful information before we can make a guess. Yeah. Before we have any useful information, yeah, so we do not feel confident to make a guess. All right. So this first strategy in problem solving, we want to do some experiments. Do simple experiments. Trials. Yeah. So we do trials. Yeah. All right. So when we do experiments, we want to choose small values for k. When k equals 1, then we look at the term a1 times x to the first. How many multiplication do we need? So very simple. Yeah. Everyone can see it, right? Yeah. 1. Only do 1 multiplication. a1 times x. 1 multiplication. All right. Now let's consider k equals 2. Now the next k value, but also very small. a2 times x squared. How many multiplications do you need? 2, right? Yeah? Yeah. 2 multiplications. Yeah. And so on. Now, after these 2 trials, do you feel you have some useful information to help you make a guess? Right? Yeah. This time, you have some information. Right? So it's not a blind guess. Yeah. You have information. Okay? You see 1, when k is 1, your answer is 1. When k is 2, your answer is 2. Now, can you make a reasonable guess after these trials? Right? Yeah. So for the general case, the reasonable guess is k. K. Okay? Yeah. Induction. Here we apply induction. Yeah. Right? Yeah. Induction may not be correct. So here, because we apply simple induction, the simple induction may not be correct. Yeah. But our guess, we do not require our guess always correct. Okay? Yeah. We just want to make our guess close to the correct answer. The closer, the better. Now, that's why it's a guess. Okay? All right. Is your algorithm efficient? Yeah. So this way, yeah, term by term, yeah. Yeah. So we can find the final value. In this way, the question, the straightforward algorithm efficient or not? We don't know, right? We don't know. Here, why at this point we cannot answer this question? Because that's the only way we know to calculate a polynomial, right? That's the only way we know to calculate a polynomial. You do not have several ways to calculate the polynomials at this point. Other than this way, do you have other ways to find the values of polynomials? Yeah. Most people may not have. If you do not have more than one algorithms to calculate the same polynomial, how do you know your current one is efficient or not? Right? Yeah. You have no idea. Because no comparison. No comparison. Yeah. One algorithm, you have no chance to compare it with other algorithms. Yeah. All right. But even if no comparison, yeah, the question, people can still study the efficiency concept for an algorithm. Yeah. So how to do it? Yeah. Find some appropriate performance number for this algorithm. Yeah. So even if just one algorithm, you cannot do the comparison, yeah, but you can define some appropriate performance number. So you can find this number to give you some information about its performance. Yeah. So what's that? What's that performance number? Yeah. What's that appropriate performance number? Yeah. Yeah. Yeah, because you want to make that performance number objective, right? Yeah. You want to define that performance number objective. Yeah. All right. Yeah. All right. So we will see that. Yeah. We will look at this question later. All right. Another question. Are we satisfied with the solution? It's hard to answer this question because that's the only one we know. Okay? If that's the only option we have, then we have to take it, right? Yeah. Only when you have more than one options, then you can choose the best one. But here, this is the only one we know. We do not have other options. Yeah. Yeah. So we don't know if we are satisfied or not with this straightforward algorithm. Yeah. All right. Yeah. So to answer this question, you need to at least to know there are some other algorithm you can use to calculate the same polynomial. At least you know other options. Yeah. So here we want to explore a little bit. Do we have a chance to find a different algorithm that can calculate the same polynomial? It's the next step. We want to answer this question. Yeah. All right. So here, to answer this question, so let's consider a very simple case. We don't need to look at the general case, right? To answer this question, we want to choose the simplest example. Yeah. Here, this is a special polynomial, right? Yeah. So this x to the k is a very special example of polynomial. So we call it monomial. So not poly, so monomial. Yeah. Single term polynomial. So it's a monomial. When we calculate the monomial, the question, do we have more than one way to calculate this monomial? No. We want to explore other options. Yeah. All right. Let's try it. Yeah. First, let's try this simple monomial, x to the fourth. So this is a very simple monomial, right? Yeah. So x to the fourth. Yeah. X to the fourth. Yeah. When we use the straightforward algorithm, x to the fourth, we just do multiplication 3 times, right? Yeah. Yeah. So we have 4 operands. They are the same x value. Yeah. To find the product of these 4 operands, 4x operands, we only need to do 3 multiplications. That's our straightforward way. All right. Now let's look at if we have another different way to calculate x to the fourth. Because we want to explore other options to calculate polynomial. All right, x to the fourth. Yeah, let's look at this way. The first multiplication, x times x equals x squared. So this is the first multiplication. All right. Second multiplication, we just use x squared because after the first multiplication, x squared value is known, right? It is known. In our second multiplication, we do not throw it away. We just reuse this x squared value. We still use this value, x squared. We do another multiplication, but this time x squared times x squared. It equals x to the fourth. In this way, we only need 2 multiplications and not 3. 2 versus 3. So it's different, right? Yeah. So it tells us there are different ways to calculate polynomials. Yeah, so we have a chance. We have other options. And we can do better. Okay? Yeah, we can do better. Yeah. So this simple example tells us we can do better than this straightforward algorithm. Yeah. Straightforward, last time I used the name brute force. Yeah. Last time I called it brute force. Method. Yeah. Okay, brute force method. Yeah. All right. Yeah. So we have hope. Yeah. Now we have confidence. Yeah. All right. Yeah. Yeah. Do we really need an algorithm? Yeah. Because after we saw the previous example, yeah. So we feel in order to do the best we can, yeah. So we really have some algorithm design work to do. We need to do some design work to find a much better algorithm for this question. Yeah. All right. Yeah. So here, yeah, I want to talk about this brute force method. Yeah. So why people? So usually, brute force method not good. Most of the time, the brute force method not good. Yeah. But why people still use this brute force method? Yeah. Because at the beginning, when you do not have good understanding on the current question, yeah, because you do not have a lot of experience. Your experience is very limited. In that situation, you need to build up your experience, right? Yeah. So this brute force method, it's the first step people use to build up their basic experience in understanding the current problem. Yeah. So it's useful. Yeah. All right. Yeah. Here it only takes addition and multiplication operations. Yeah. So now, when we study the performance, here, performance or efficiency, yes. So here, for the wording, so the old time of algorithm context, people use the word performance. Yeah. The current wording, so people change to efficiency. Efficiency. Okay. All right. Yeah. So yeah. So we most of the time we will use efficiency. Yeah. Sometimes we use performance. Yeah. Yeah. but we mean the same thing here. Yeah. All right. Yeah. Now, another question. Do we still have any room to manipulate the additions and the multiplications? Yeah. So here the question. The question. Yeah. Remember, we want to explore different algorithms. How to make our algorithm different. So that understanding we need to address. How to make our understanding different. Yeah. All right. To make our understanding different, we change the way of calculating additions and multiplications. So, what do you mean changing the ways? Yeah. Because we can evaluate additions, multiplications in different orders. Different orders. You have freedom to choose your evaluation orders. Yeah. Orders of what? Orders for your operands, right? Yeah. So orders for the operands. Okay? Order of operands. You have freedom to choose. Yeah. At this point, you may not understand this idea well, yeah, because it's too abstract. So when I talk about these ideas, in your mind, you feel it's quite abstract. Yeah. But later, when we do some trial work, experiment work, yeah, so you will understand better. Yeah. All right, so let's see. We will get to that point. Yeah, order. Okay? Yeah. All right. Do we have other orders to apply operations? Yeah. Yes. Yeah. So, yeah, we have freedom. We have a lot of freedom to change the orders. Yeah. Yeah. But we will get there. Yeah. Get to that point. All right. Can we use execution time? Remember, when we talk about some measure of efficiency, yeah, here, when we talk about measure of efficiency, one way to measure the efficiency, we can use execution time, CPU execution time. When you run your program, you clock it, yeah. So you can get response time, right? Yeah. So in that way, this is a measure of efficiency. It is objective, but it's not. It's unstable. Unstable. Yeah, very easy to say unstable. Because different people, they use different computers. And the computing powers for different computers vary greatly, right? Some high-end supercomputers, some low-end, older machine, very slow machines. Yeah. So unstable. This measure is unstable. So it's not a good measure for efficiency. Not good. Yeah. People want to choose a stable measure. So it does not rely on your computing hardware. Okay? Fast computer, slow computer, doesn't matter. Same quantity on fast computers or slow computers. That's a stable measure. Yeah. All right. Yeah. So execution time is not a good choice. Yeah, right? Yeah. So different machine. Yeah. Even the same machine, when you use different programs. Yeah. Yeah. Program. So we refer to the software side. Yeah. Machine hardware side. Yeah. So from the hardware side, from the software side, yeah. Software coding, right? Coding. Even the same algorithm, different people have different ways to implement the same algorithm, right? Yeah. Because the way you organize your data, so the way you set up, okay, the resource, the way you use your resource, quite different. Yeah. So from the software side, the response times could be different. Yeah. All right. That's why we don't like to choose this unstable measure for our efficiency. Okay? Yeah. So the ideal measure should be stable one. Yeah. All right. So how to find a stable measure for the efficiency? Yeah. The idea is very simple. Using number of additions and number of multiplications. Counting numbers. Yeah. Here, do counting. Yeah. The counting numbers are stable, right? Yeah. So for different machines, you have the same counting number. Okay? Fast machines, slow machines, from software side, program implementations, because you have the same counting numbers. Yeah. So that's a stable, better measure for efficiency. All right. But there is another question. Yeah. Because when we count the number of additions, yeah, so let's say there are m additions and there are n multiplications. Yeah. And these two numbers, they have different meanings. Because additions and multiplications, execution times for these two operations are quite different. Yeah. So we cannot add m and n. Yeah. It's not fair, right? Yeah. We know doing one addition in a computer CPU is much faster than one multiplication in CPU. Yeah. So we cannot add these two counting numbers directly. They're not equivalent. Yeah. So we need to do some work to bridge these two operations. Yeah. Bridge them. Yeah. All right. So here we want to add some reasonable assumptions. Yeah. Sometimes in problem solving, we may need to add some assumptions, but we don't want to change our problems, change the difficulty of our problems. Now, we want to, maintain the intrinsic properties of the original problem, but we want to make the situation more fair, right? Yeah, fair. Yeah, because the measure number, when we talk about measure number, we only want one number, right? So measure should be one number as the measure. But here, if you have two numbers, m and n, how to represent your measure in a simple way? You cannot. So for that reason, we want to add some reasonable assumptions. So what's that? Yeah. Yeah. Each addition, we assume each addition takes 1 unit of time. That's okay, right? Yeah, 1 unit. Yeah. Certain unit. Yeah. Certain amount of time. But that's 1 unit. Okay? Yeah. So we compare the total units of time used to calculate this polynomial. All right. Then, how much units of time we need for a multiplication? Yeah. Here we assume 10 units. Yeah. So why assume 10 units? Because when we look at the CPU, yeah, inside CPU, yeah, when we do integer multiplications, when we compare integer multiplications and integer divisions, the CPU time used for these two operations, the ratio is 10 to 1, approximately 10 to 1. Okay? Yeah. It may not be exact 10 to 1. Yeah. Approximately 10 to 1. Yeah. So here we use this assumption. Okay? Yeah. All right. B.2. Estimate the cost. Now we need to evaluate the cost. All right. Subproblem 1, count the number of additions. Yeah. So let's do the counting, number of additions. Yeah. All right. Let's do our first try. Yeah. This first subproblem, we only count the number of additions. We do not count number of multiplications. Okay, all right. Can you see, yeah, because here the n is a parameter. So we use n parameter. Yeah. It is known. No. Suppose it is given. Yeah. So with a given n parameter number, yeah, how many additions do you need when you apply the brute force algorithm? Brute force, yeah, here. Counting, that's a simple counting question. Okay, all right. Yeah. Here I want to introduce some problem solving skill or technique. Okay, yeah, simple technique here. Here we the strategy. Yeah, we apply strategy. The strategy, same strategy we applied before. Okay? Yeah. Work on the easier parts first. Yeah. In problem solving, when we need to do multiple tasks, we want to work on easier tasks first. Yeah. So remember, in our first class, we took the strategy in our first class. All right. Yeah, so the hard point, yeah, the hard part, yeah, because here, why, when we count the number of additions, for some people it's hard, because we skip many terms. So the ellipsis sign here, because we cannot list all the terms, right? Yeah. So we have to skip most of the terms. Yeah, we know the meaning, but when we do that, there is one question. It's hard to keep track of the data, right? Yeah. Here there is a question, hard to keep track of the data. Yeah. Yeah. So first technical problem we need to solve, we want to find a way to keep track of the data. Okay? Yeah. All right. How to find an effective way to keep track of those invisible terms? Yes. So we need to solve this small technical problem. Okay. All right. So let's take a break. Yeah. So let's take a 10-minute break.